Welcome back, operators. Let's dive right into today's expert masterclass. We're going to methodically break down exactly how to diagnose and cure critical scaling failures in ultra-pure water systems. You know, if you've ever been staring at the screens, watched your resistivity numbers absolutely tank, and felt that sudden knot in your stomach, well, you're in the right place. We're going to tackle this whole process systematically.
As someone who spent 20 years running UPW operations, I want to walk you through my exact 6-step framework today. We'll cover our intro to EDI technology, incident symptoms and recognition, formulating hypothetical causes, investigating the root cause, executing troubleshooting steps, and finally, a summary and final thoughts.
All right, part 1, intro to EDI technology, the baseline of ultra-pure water. Because, look, before we can even attempt to fix a broken system, we've got to establish exactly how a healthy ultra-pure water plant operates. You literally can't spot an anomaly if you don't know the baseline.
So picture your standard UPW process flow. Water comes in, passes through your multimedia filters, hits the reverse osmosis unit, and then enters our main focus area for today, electroionization, or EDI. Notice how EDI sits right there as the absolutely critical polishing step right before UV sterilization. It is heavily relied upon to deliver that pristine product water, typically pushing greater than 15 megaohms per centimeter. Basically, if this step fails, the whole plant's output fails.
And this is exactly why EDI is such an elegant technology. Inside the module, you've got ion exchange resins sandwiched tightly between ion-selective membranes. Under a DC electrical field, this incredible process called water splitting happens. The electrical current literally tears water molecules into hydrogen and hydroxyl ions, which then continuously regenerate your ion exchange resins. Because it's constantly refreshing itself, it can continuously pull out those stubborn, weakly ionized species, like silica and carbon dioxide, without ever needing to take the system offline for hazardous chemical regenerations. Section 2. Incident symptoms and recognition, the anomaly. Okay, so we know how it's supposed to work, but what happens when it just doesn't? Let's talk about that heart-stopping moment in the control room.
Boom! Right here, this is your ultimate red flag. Your product water resistivity has plummeted from a nice, healthy 15 or 18 megaohms straight down to below 5 megaohms per centimeter. When you see a drop that severe across an EDI unit, it is screaming at you that a massive ionic breakthrough has occurred. The module is completely failing to polish the water.
But beyond just the scary numbers on your screen, you've got a physical nightmare happening inside: hard scaling. Calcium, magnesium, and polymerized silica are actually precipitating directly onto your resins and membranes. And what makes this so incredibly destructive is that this scale acts as an electrical insulator. Remember that vital DC current we need for water splitting? The scale blocks it completely. You're going to see increased electrical resistance on the module, and eventually that scale will physically choke the internal channels, crushing your product water flow.
Moving to part 3, formulating hypothetical causes. Time to brainstorm the culprits. See, when a module scales over, a seasoned operator doesn't just panic. They start forming hypotheses. Because here is the golden rule you need to remember. EDI failures are almost never EDI problems. They are almost always upstream failures.
So let's look at your first 2 prime suspects. First up, an RO hardness slip. If your reverse osmosis permeate quality degrades and lets residual calcium or magnesium slip into the EDI, it's going to precipitate right there in the concentrate chambers. Second suspect, a degassing failure. Unremoved carbon dioxide acts as a massive anionic load. CO2 is like a space hog. It competes heavily for ion exchange sites and completely overwhelms the resin's capacity to pull out other critical ions like silica. And your third prime suspect is actually a structural vulnerability in the plant's design. Are you operating without a mix bed or MB guard? If you're missing an upstream polishing guard to buffer the EDI from sudden ionic spikes, your highly sensitive EDI membranes are just sitting there taking the full direct hit of any upstream upset. So we've got 3 solid hypotheses: an RO slip, a CO2 overload, or a lack of buffering. But here's the real test for us as operators. How do we isolate the true root cause without guessing and without needlessly taking the entire plant offline? Well, we need hard proof.
Part 4, investigating the root cause, the diagnosis. We're stepping out of the hypothetical phase now, and we're going straight to the cold, hard data from our feed water parameters.
You have to go test your EDI inlet water immediately. Don't pull last week's logs. You need a real-time, live sample. You need to verify that feed water hardness is virtually at 0. You've got to check your RO permeate quality for any kind of degradation. Confirm that your feed water silica is strictly under 0.5 parts per million. And grab a fresh measurement of your incoming CO2 levels.
Now line up your real-time data right against these strict industry targets. Hardness must be near 0, or your risk of calcium and magnesium scaling goes through the roof. Silica has to be strictly below 0.5 ppm, otherwise you're risking a glass-like silica scale that is incredibly tough to clear. And CO2 must be exceptionally low. If any single one of these parameters is running high, you've found the exact smoking gun responsible for your scaling.
All right, part 5. Executing troubleshooting steps. The cure. Now that we've found the upstream bleeding and we know exactly what caused the scale, we have to cure the module and safely get production back online.
Here is your operational cure, step by step. First, you absolutely must correct the upstream RO or feed issue. Seriously, do not clean the EDI until the feed water is perfectly stabilized. Otherwise, you're just going to scale it all over again tomorrow. Second, you execute a highly specific clean in place, or CIP, acid and complexing wash to strip the scale out. Always strictly follow your manufacturer's specs for this. And third, to make sure this nightmare doesn't happen again, retrofit a mixed bed guard upstream.
Looking at the system flow diagram here, you can see exactly how the cure gets applied. The CIP chemicals have to be carefully, deliberately circulated through both the feed and the concentrate channels. You're using a low pH acid wash to dissolve those insulating calcium carbonate layers. But, it requires precision. Too aggressive and you'll permanently fry those delicate ion-selective membranes. You are just trying to dissolve the insulators so your DC current can flow freely once again. Bringing us to part 6, summary and final thoughts. Let's do a quick debrief and lock in what we've learned today, so this anomaly never catches you off guard on your watch again.
Here are the key takeaways you really need to commit to memory. EDI is brilliant, but it is deeply, deeply sensitive. It requires incredibly strict feed parameters, like holding that silica under 0.5 ppm. When scale does form, it acts as an electrical insulator, effectively killing your water splitting process and destroying your resistivity. Routine monitoring of your RO permeate is genuinely the only way to prevent a failure. If it does scale over, CIP acid washes can recover the module, provided you catch it in time. And adding those mixed bed guards, that offers absolutely critical secondary protection for your entire plant.
I want to leave you with something I've lived by for 2 decades in this industry. Prevention upstream is the only true cure for downstream scaling. Seriously, if you are actively treating the EDI module, you are already way too late. You must treat the water flawlessly before it ever reaches the unit. So I'll leave you with this final thought as you head back to the control room. Ask yourself right now, are your upstream RO and degassing units genuinely protecting your critical EDI modules? Go pull your plant's data today, verify your parameters, and make absolutely sure your system is running as flawlessly as it was designed to. Thank you so much for joining me in this Masterclass Explainer. Keep those resistivity numbers high, and I'll catch you on the next one.